Welcome to this explainer. Today, we're going to completely decode the invisible mathematical and biological rules that govern how every single species on Earth grows, survives, and, well, ultimately hits a wall. Whether we're talking about a microscopic bacteria colony on a petri dish or a massive herd of elephants in the savannah, life operates by a remarkably strict set of ecological laws, and honestly, understanding them is absolutely fascinating. Let's kick things off with a massive question that biologists have grappled with for centuries. If living things are literally designed to multiply and spread, why isn't the Earth completely overrun by just one type of animal or plant? I mean, why aren't we just swimming in a sea of rabbits right now, or suffocated by an endless blanket of algae? There are hidden forces keeping every population in check, and that's exactly what we're going to unpack. Here's our roadmap for today's deep dive. Number 1, the math of life. Number 2, hitting the biological limit. And number 3, the human factor. Let's get right into it. Starting with Section 1, the math of life, and visualizing population growth. Okay, to truly understand the grand scale of ecosystems, we first have to look at the basic blueprints. How do scientists actually measure a population and track how it changes over time? Well, they use 4 key metrics. First, there's simple population size, just the sheer number of individuals. Next is population density, which tells us how packed together those individuals are in a specific area. Then we have dispersion, basically the spatial pattern of where they live. And finally, age structure, which tells us the proportion of individuals in different age groups, like, how many are actually at reproductive age. Now, the overall growth rate of all this fluctuates based on a pretty straightforward equation. Births and immigration add to the population, while deaths and emigration take away from it. When you map out population growth, you usually see one of two totally different paths. First, there's the theoretical J-curve of exponential growth. This is what happens when a species has unlimited resources, no predators, and no disease. The population just explodes endlessly upwards. But we live in the real world, and out here, resources eventually run out. That brings us to the realistic S-curve of logistic growth. In this scenario, limiting factors like predators, parasites, and competition eventually step in, causing the population growth to flatline and stabilize. Moving on to Section 2, hitting the biological limit, or what I like to call the invisible walls of nature. So how do these math curves actually translate into real-world biology? The crucial takeaway here is that every single environment has what biologists call a carrying capacity. This is the absolute ceiling. It's the maximum number of individuals that a specific ecosystem can support over the long haul. And this number isn't just randomly assigned. It strictly depends on the physical size of the organism, its trophic level, meaning where it sits on the food chain, and the physical size and type of the ecosystem itself. Now, to maintain this carrying capacity and prevent populations from completely destroying their own habitats, ecosystems enforce restrictions. We call these limiting factors. These are the environmental forces that restrict a population's growth rate, causing it to slow down, stop entirely, or even decline. And they are brilliantly divided into 2 distinct categories based on population crowding: density-dependent factors and density-independent factors. First up, density-dependent factors. Think of these as nature's biological crowd control. They kick in heavily to restrict growth rates really only when a population gets too crowded. Imagine a super dense herd of deer. If they are packed tightly together, disease is going to spread like wildfire. Predators like wolves are naturally drawn to that all-you-can-eat buffet. And intense competition for a shrinking supply of grass will naturally weed out the weakest members. On the flip side, we have density-independent factors. These are essentially random acts of nature that limit all populations in the exact same way, completely regardless of how crowded or sparse that population is. A severe freeze, a catastrophic flood, seasonal shifts, or human activities like clearing out a forest, these events will decimate a population of 5 individuals just as easily as they would a population of 5,000. Nature doesn't play favorites here. But sometimes the primary limiting factor isn't a dramatic natural disaster or a hungry predator. Sometimes it's literally just the dirt. We call these limiting nutrients. Elements like nitrogen, phosphorus, and potassium are often naturally scarce in the soil and require a lot of slow, complex transformations to become usable. And because producers, like plants, rely entirely on these specific nutrients to grow, their scarcity strictly dictates the productivity of the entire food web, right from the bottom up. Which brings us to Section 3, the human factor. Are we somehow bypassing the rules? With a firm grasp of carrying capacity and limiting factors, let's pivot to the absolute most fascinating and complex case study on Earth: us. Over the past few centuries, the human population has exploded at a rapid pace. If you track our historical data, we're currently exhibiting a growth curve that looks incredibly suspiciously like that exponential J curve we discussed earlier. We seem to utterly defy the standard biological limitations that keep every other species on the planet in check. So, how in the world did we do this? Well, we used our intelligence to systematically dismantle our natural limiting factors. Through massive advancements like modernized agriculture, which totally bypassed traditional food scarcity, alongside vast industrialization, improved sanitation, life-saving medication, and cutting-edge tech, we effectively removed the biological crowd control that nature normally imposes on a species. And this brings us to an incredibly vital question, one that scientists and ecologists debate endlessly. Have we permanently bypassed the laws of ecology? Or have we simply delayed hitting our ultimate carrying capacity? Because remember, no species gets to enjoy limited resources forever. The rules of the Earth still apply. To avoid hitting a catastrophic biological ceiling, a sudden, devastating crash at the top of an S-curve, our survival heavily relies on shifting our focus toward renewable resources. These are biological assets that can regenerate fast enough to sustain our massive human numbers without permanently depleting the Earth. We're talking about carefully managing trees, fish populations, clean water, and oxygen, so they can safely replenish themselves naturally. A really brilliant illustration of how we can intentionally mimic nature's own limiting factors to our advantage is through waste recycling. When we use natural decomposers to break down our lawn and garden waste into compost, we are artificially looping those crucial limiting nutrients directly back into our soil. This highly efficient process preserves precious landfill space and drastically reduces our dependency on artificial fertilizers. We essentially become an active, sustainable part of the ecosystem, rather than just a drain on it. I want to leave you with this provocative thought to cap off our explainer today. We've seen that the math of life is completely uncompromising. So as our population continues to climb, mastering population dynamics isn't just about understanding nature or passing a biology test. It is quite literally the fundamental blueprint for designing humanity's long-term survival. If Earth's resources are indeed finite, what limits will we actively choose to set for ourselves before nature steps in and inevitably sets them for us? Thank you so much for joining me on this deep dive. Keep questioning, keep learning, and I'll catch you in the next one.